So, when you're looking out the window of a passenger jet flying straight through a brutal winter storm, and you just kind of wonder, how does this massive metal machine just shrug off these freezing conditions? Well, today in this explainer, we're diving right into the fascinating hidden engineering that keeps commercial flights totally safe from some of the atmosphere's most dangerous weather. But first, before we get into the actual nuts and bolts of the machinery, we really have to set the stakes. What actually happens when an aircraft moving at hundreds of miles per hour slams into a cloud of sub-zero water? Now, you might think the air up there is just filled with solid snow or maybe ice crystals, but honestly, the reality is a lot stranger and honestly way more dangerous. Because we are dealing with something called supercooled water. Think of it literally as a trap waiting to snap shut. Under certain atmospheric conditions, water droplets in the clouds actually drop below freezing, but they don't turn into ice. Their surface tension holds them together as a liquid. But the very second the fast-moving leading edge of an airplane smashes into them, that surface tension breaks, and bam, they instantly flash freeze into solid ice right onto the plane's surface. Here is the flight path for this explainer. 1. The high-altitude threat. 2. Detecting the enemy. 3. Anti-icing solutions. 4. De-icing solutions. And 5. Keeping the windshields clear. Section 1. The high-altitude threat, the physics and dangers of ice. Just to give you some environmental context, as a plane climbs up through the troposphere to a standard cruising altitude, say around 38,000 feet, the temperature absolutely plummets. The aircraft passes right through this perfect freezing zone where all those supercooled liquid droplets are just hovering, waiting to grab onto an airframe. And let's be clear, ice is not just a minor inconvenience up there. It violently alters the plane's aerodynamics. First off, it malforms the airfoil, meaning the actual shape of the wing changes, which drastically decreases the lift keeping the plane in the air. Second, it slaps a ton of extra dangerous weight onto the structure. And worst of all, it rarely freezes evenly, so you get this severe unbalancing effect that makes the aircraft incredibly hard for the flight crew to control. We're basically dealing with two main villains here. First is clear ice, which comes from larger water droplets, like rain. It freezes as a smooth, solid sheet. It is heavy, it's dense, and it's notoriously hard to get off. Contrasting that is rime ice, which forms from smaller drops, like a light drizzle. Rime ice is rougher, highly irregular, and looks white because it actually traps air inside as it freezes, making it a bit lighter than clear ice. Just imagine the incredibly smooth, sleek, leading edge of a wing suddenly deformed into a jagged, heavy, blunt mess. Try picturing the air attempting to flow smoothly over that. It can't. And that loss of smooth airflow is exactly what aeronautical engineers are fighting against. Section 2. Detecting the enemy. How aircraft sense the environment. Now, sure, pilots can always just look out the window to spot ice building up, but modern aircraft rely on serious precision. They use automated ice detector probes, usually mounted right on the nose. The moment ice starts forming on that tiny little strut, it triggers an alert light in the cockpit. And on a lot of modern jets, it bypasses the crew completely and automatically kicks on the ice protection systems the second it senses danger. Section 3. Anti-icing solutions. Preventing ice from forming. Once the system knows there's a threat, the first line of defense is basically a technological force field. We turn on our anti-icing equipment before ice even has a chance to form. One of the primary ways we do this is with a thermal pneumatic system, which actually bleeds hot, pressurized air directly off the engine compressor at 41 psi. An ejector blasts that scorching air into distribution tubes along the leading edge of the wing. To manage that intense heat, flush-mounted scoops pull in cold outside air to mix with it. And then this thermal shield travels the length of the wing before venting safely overboard. We are talking about blisteringly hot temperatures maintained inside the wing. Just to operate effectively, it needs to hit at least 140 degrees Fahrenheit, but it can easily reach 350 degrees on the inner sections of the wing. To put that in perspective, that's hot enough to bake a cake right inside the wing's leading edge. It takes extreme heat on the inside to fight the extreme sub-zero cold on the outside. But hot air isn't the only trick up our sleeves. For sensitive external instruments, like pitot probes or angle of attack sensors, engineers use thermoelectric systems, basically running electric currents through conductive materials to heat them up. There's also this wild technology called a weeping wing. It literally pumps an antifreeze chemical through a microscopic mesh screen embedded right into the wing. The wing essentially weeps fluid, which mixes with those super cooled water droplets we talked about, lowering their freezing point so the water just harmlessly flows right off the plane.
Section 4. De-icing solutions, breaking the ice.
But okay, what if ice still manages to strike the aircraft? Maybe a system kicked on late, or the storm is just that severe. This is where we need to make a really crucial distinction. If anti-icing is your invisible preventative force field, de-icing is your brute force physical weapon. It is designed to aggressively break apart and shake off heavy ice that has already clamped onto the airframe. The most common way to do this is with pneumatic de-ice boots. During normal, clear flight, a constant vacuum suction holds these thick rubber boots completely flat against the wing so they stay perfectly aerodynamic. But when activated, that vacuum drops, and boom, 17 psi of pressurized air violently inflates the boots. They literally swell up and physically shatter the rigid ice shell. Then they instantly deflate and suck tight against the wing again. I always find it genuinely amusing that on a multi-million-dollar high-tech flying machine, keeping these vital boots working comes down to really basic rules. Mechanics have to treat them like fragile rubber. You can't drag a fuel hose over them, you absolutely cannot rest your wrench on them, and to clean them, just a little mild soap and water. It's a fun reminder that sometimes advanced aerospace engineering is surprisingly delicate. Now, for propeller-driven planes, you obviously can't pump hot engine air out to a rapidly spinning blade. Instead, they use a slip ring and brush assembly that transmits an electric current directly to a heated boot cemented onto each individual blade. This melts the inner layer of the ice just enough that the massive centrifugal force of the spinning propeller just flings the ice right off, keeping the engine running efficiently. Section 5. Keeping the windshield clear. Rain control solutions. Finally, let's step away from ice for a second. Because if a pilot can't see the runway through a massive rainstorm, none of that wing tech matters. To maintain a crystal clear view, planes use a multi-layered approach. They've got heavy-duty electric windshield wipers, sure, but they also use crazy advanced hydrophobic surface coatings. These coatings literally change the surface tension on the glass, forcing rain to instantly beat up and get violently blown away by the wind. Add in electric heating grids to stop frost and fog, and the pilots never lose their window to the world. So the next time you're sipping a coffee at a cozy, pressurized cabin while flying through a brutal winter storm, just think about the invisible symphony of protection happening outside. Electric grids are glowing, scorching hot engine air is surging through the metal wings, and rubber boots are expanding to shatter incoming ice. It's an absolute war of physics, keeping the elements exactly where they belong, outside. Thanks so much for joining me on this explainer, and next time you fly safely through a freezing storm, ask yourself, which invisible, heated, and shape-shifting systems are silently battling the elements right outside your window?